Let's talk related rates, which is a section of calculus that is usually tied to geometry. If you are a random passerby on the internet and you want to follow along with this with a worksheet that I physically handed my students, like a fill-in-the-blank notes sheet, you can go to bit.ly/related rates intro and print it there. So let's dive into related rates. It is typically tied to geometry, does not have to be, but before we get to the calculus twist to geometry, let's talk about old geometry. And old geometry was very nice because your shapes stayed the same size. They did not change. They just sat there nice and pretty. And an example like this one, if you want the volume of a sphere with a given radius, you just plug the radius into the formula for the volume of a sphere, and there you go. And hopefully your geometry teacher always stressed units. If units are provided, please include units in your answer. And you would have an answer of that. I do not feel like simplifying or cleaning that up in any way. That is your old geometry. That's how things used to be done. Well, in calculus, we change that. So calculus, the most simplified version or definition of calculus I can give you is it allows us to study things as they change. You can look at things as they are increasing or decreasing and measure the rates of change of those increases and decreases. And related rates problems allow us to solve these problems, and they are frequently tied to geometry. We can solve these geometry problems and analyze these geometry problems as the given dimensions and measurements increase or decrease. So your sphere will no longer stay a sphere with a radius of 8. That radius could be increasing or it could be decreasing. You can think of it like a balloon that's being inflated. The radius of that balloon, assuming you can keep it a perfect sphere, would increase as you blow the balloon up. And that's kind of what I'm looking at here with this example. The radius of a sphere increases at 2 meters per second. Find the rate that the volume of the sphere increases at the instant the radius is 5 meters. So what I like to do first, anytime I have a word problem, related rates or optimization or anything, I like to kind of annotate my problem and take all the information out of the paragraph and list it in a bulleted list of information. And the first thing I see that I want to pull out is the radius of the sphere increasing at 2 meters per second. Anytime I see the word increase or decrease, I am thinking derivatives, especially in a calculus class. And so the radius is what is increasing. So I could say that r prime, the derivative of the radius, and we know that it is increasing at 2, always make note of units, meters per second. And there's nothing wrong with writing r prime. However, I'm going to make one little change. This unit here, the meters per second, I'm going to change the way I write r prime, and instead of r prime, I'm going to use Leibniz notation, and we are measuring the change in radius with respect to time. This is meters per second, so I'm going to label that as dr dt, and that's a reminder that I am measuring things as time changes. So let's move on to the next piece. Find the rate. So here's the question. Find the rate the volume increases. So I'm trying to find the rate the volume increases, which could be V prime, but I'm going to call that dV dt, the rate the volume increases. And then they give me a measurement right here at the instant the radius is 5 meters. So I'm looking at a point in time when the radius itself, not the radius is changed, not dr dt, but the radius itself is 5 meters. And anytime you are given a measurement like that, you want to think, does that measurement change or is it constant? In this case, the radius is changing. They already told you that the radius is increasing. And things that are changing, I like to put like a little flashbulb bang thing around that just to remind myself that the radius is changing. And we're going to talk more about that in a minute. So there is all the given information. I pretty much have the entire question right here listed in these nice little bullets. And so next thing I have to do is find a formula that can tie all of this together. And we are talking about the volume of a sphere, which we just did on the previous page, is 4/3 pi r cubed. And we're looking for the rate of change of the volume. We are given the rate of change of the radius. So I'm going to need to introduce a rate of change here by differentiating this equation. So I'm going to find the derivative of this whole equation with respect to t. And this brings in implicit differentiation. I'm doing the derivative with respect to t. V is not a t. So the derivative of v would be dv dt. On the right side, it's kind of ugly looking, but 4/3 and pi are constants. So I'm just going to leave those alone. And then the derivative of r cubed would be 3r squared, but r is not a t. So I have to give it the implicit treatment, dr dt. And then after you find the derivative, you start plugging in everything that you are given. I'll look at my given information. I know that dr is 2. I know that r is 5, and I'm trying to solve for dv/dt. So I'm not going to plug anything in for dv/dt. I'll just leave that alone. I will plug in, oh, look, I can cancel 4/3 times pi times 3. Those 3's will divide out. Get rid of those. So I'm left with 4 pi r, which is 5. Now I can plug the 5 in. I can plug that 5 in now that I've taken the derivative. And dr/dt is 2. And that ends up being 4 times 25 times 2. That is 200 pi. And then I always want to include units in my answer. And the way I do that is I simply think about what I found. I found a change in volume over a change in time. And so my numerator unit is going to be a unit for volume. That would be meters cubed. And my time unit is seconds. And there is your answer for this particular problem. The volume is changing at a rate of 200 pi meters cubed per second. So when it comes to related rates problems, some things to make note of, some things to remember as you are pulling information out of the paragraph. So first, make note of, or when making note of your given measurements. So in the previous problem, we knew that the radius was 5. Make note of whether that dimension is changing or if it is constant. You want to make note of whether things are changing or if they are constant. If the dimension is changing, so the radius was changing, so you've got to make sure you assign that a variable. It has to be given some kind of variable to represent that it does change, and you do not plug in those variable measures until after you differentiate the equation. And that's exactly what I did on the previous problem. I knew that r was 5, but I do not plug in 5 early. I wait till after the derivative, then I can plug in the 5 because 5 is or the radius is changing. It's not constant, so we do not plug that in early. If the measurement is a constant, and that will happen on occasion, then you can actually plug in that measurement before you differentiate, and that would make the derivative a little bit easier because it knocks out a variable. It replaces a variable with a constant. So if you have a measurement that is constant, then we will plug that in early before the derivative. And then finally, make sure that when you are done that you have units attached to your final answer if units are provided. Sometimes units are not provided, especially if it's not a problem tied specifically to geometry. So make sure units are provided or units are given. And so let's go to my last example. I only had 2 examples I wanted to talk about. So this is a fairly typical calculus problem. We have a 10-meter long wooden plank leaning against the wall. So here's my wooden plank. It's leaning against the wall. It begins to slide down the wall, and as it slides down the wall, the bottom will slide away from the wall. So it tells you the top of the plank is moving down the wall at 3 meters per second. At what rate is the bottom of the plank moving away from the wall? So what is the rate that this thing is changing down here? When the top is 8 meters from the wall. So there's a lot of information there. And when I'm looking at this, I'm thinking, and I'm looking at this shape, I'm looking at this diagram here, what's changing and what's constant? I see one constant. The plank is 10 meters long. That plank is not changing length. The plank is not growing, it's not shrinking. That is constant. And because that is constant, I'm going to go ahead and put 10 right here. Now, if the hypotenuse, if that measurement changed, I would have to call it a h for hypotenuse or whatever you want to call it. So there's a constant of 10. I'm going to go ahead and plug that in. The top of the plank is moving down the wall at 3 meters per second. So I'm going to make a note right here that we are moving down at 3 meters per second. At what rate is the bottom of the plank moving away from the wall? So we're looking at this bottom piece right here. How fast are we moving away from the wall? I'll just put a question mark. That's what we're looking for. When the top of the plank is 8 meters from the ground. So when the top, so here's the top when we're 8 meters from the ground. So we just got given we were given another direct measurement, 8 meters. This measurement right here is 8 meters. Is this always 8? Can I put an 8 here? Does that change? And it changes. So I don't put the constant in there. I don't put that measurement until later. Since that changes, I have to give it a variable. I think that h makes sense because I'm looking at a triangle, and that will be the height of the triangle. And while I'm assigning variables, down here at the bottom, this dimension changes as well, and that is the base. I'm going to call that b. And so I have a few things here. I want to make a few more notes here. I have the top is sliding down at 3 meters per second. That is a rate of change. Something, d something, dt, is changing at 3 meters per second. Something is changing at 3 meters per second. And if you look at that, the 3 meters per second is a vertical change. So that's going to have to be the change in h. The height of that triangle is changing at 3 meters per second. And then one more thing you have to think about that I did not think about on the previous page, that height, dh dt, that measurement of h is decreasing. And because h is decreasing, we have to note that that is a negative change. dh dt is negative 3 meters per second. The question is asking us to find, they ask us to find, where are we? Find the rate that the bottom of the plank is moving away from the wall. So that we're looking for this. So we're trying to find d something, dt, and the rate that we're looking for is the horizontal change, which will be the rate that b is changing. And just in my mind right now, I notice that b is increasing. The length of that base will increase. So I should get a positive answer for db dt. And when the height, or when the plank is 8 meters from the ground, so that is h. So we're looking at a point in time when h is equal to 8. H is equal to 8, and that is not changing. Or I'm sorry, that is changing. So I put a little flashbulb around it. And I finally have all of the information pulled from the paragraph. I have all the information pulled from the paragraph. I have my little diagram here, and I need to tie all this together with some type of an equation. And the equation that can tie all this together, we're not going to use area, but notice that in this triangle, everything in this right triangle is about the side lengths, and there's a nice, cute formula that ties your side lengths together, and that is your Pythagorean theorem. B squared plus h squared equals 10 squared. And once I have that formula, now I'll look and see, can I plug anything in? I can't plug anything in yet because h and b are changing. They have to remain variables. 10 is a constant. I already have that in there. So I have all that. Now I am ready to think derivatives. So if I want dB dt, I'm going to have to introduce a derivative, a rate of change here, and that will be done by differentiating the equation. And so the derivative of b squared is 2b, but we are differentiating with respect to t. B is not a t, so I have to tack on the dB dt. The derivative of h squared will be 2h dh dt. And then 10 squared is a constant, and the derivative of a constant would be 0. And for Pythagorean theorem problems, before I start plugging in numbers, I can do one tiny thing to clean this up a little bit. I could divide everything by 2. And if I divide everything by 2, that makes my derivative just an itty bitty 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 bit cleaner. So there is my derivative, and now I'm ready to start plugging in everything I know. I'm looking at this. I do not know what b is. dh dt, what is that? That's a b. That's a really bad b. That's db dt. What is that? Whoa, what's wrong with my writing here? dB dt, there we go. So dB dt, that's what I'm looking for. So that's going to remain dB dt here. Plus h, they told us that h was 8. I can plug that in now. dh dt is negative 3 equals 0. And we have a little bit of a problem. I don't know what b is. I have to find b. This is something that happens relatively frequently in related rates. You find the derivative, you start plugging in, and you realize you are missing a little bit of information. And so I now need to find b. And usually, there are some exceptions to this, but a lot of times to find missing variables, you simply go back to your original equation, b squared plus h squared equals 10 squared. And we can solve for b at this instant when h is 8. So if h is equal to 8, I could say b squared plus 8 squared equals 10 squared, and you will end up with b equaling 6 at this point in time. Now, that's not always true, but that is true at the same time h is 6, or I'm sorry, h is 8. So now I take out the b, I can replace it with a 6, and now we are ready to solve the equation. dB dt is going to equal, I'm going to add that 24, I'll divide by 6, and it will be 4. Now for units, this is the base. Base will be measured in linear units. That will be meters per, and we are doing seconds. And there is our answer. The base of this triangle, or the bottom of that the bottom of that plank is sliding away from the wall at 4 meters per second. And there is an introduction to some related rates, and the second one got a little bit wonky, but there we are. Hopefully you understand a little bit there.